MS in engineering physics from Dartmouth College and a PhD in mechanical engineering from the University of New Hampshire. He serves as the Deputy Director of the Center for Solar Terrestrial Research, Polar Engineering Development Center, where he oversees the operation and on-site service of NGIT's Antarctic stations for space research. He's also a science team member of the RB SPICE instrument on board NASA's Van Allen probes mission, studying Earth's radiation belts. Through these efforts, he explores his research interests of using ground-based and satellite data to analyze interhemispheric geomagnetic response to solar wind, emic ULF waves, and wave propagation in the ionosphere. He's an all-rounder in the space physics community, mechanical engineer, an electric engineer, and a space physicist. He has served as a GEM focus group leader and is passionate about community outreach, as he has given multiple lectures to students in kindergarten to high school. And he is also interested in bringing opportunities for scientific engagement to a larger community with art and science collaboration, and has helped design an interactive art installation driven by magnetic field data from either real-time or from past measurements. In 3D physical space, viewers can reflect upon the ever-changing nature of the Earth's magnetic fields and the sun. So please join me in welcoming Dr. Hyomin Kim.
Hey, thank you, Jodie, for introducing me. Good morning, everyone. My name is Hyomin Kim from NGIT again. So here I'm going to be talking about interhemispheric asymmetries in MI coupling. So just to give you some background, since the beginning of my PhD project, my job was to go south. It may sound strange, but I actually was deployed to Antarctica to. Okay. So my project involves some deployment of ground instrument in Antarctica. So naturally, I've been involved in this kind of interhemispheric work, thinking that what we see in the south is not mirror image of what's happening in the north. So here I'd like to acknowledge many people, including our NASA LWS team members, Ilya, Zonghua, Doha, as part of the LWS project. Also, I've been running with Bob Lysak sitting over there, and I don't know if Tomoko Maso here. We've been running a interhemispheric focus group for 5 years with 1-year extension due to COVID. And many others. I'm sure I forget many important people that I should thank here. So the first thing that you can think of as interhemispheric asymmetry is the very famous the auroral image taken from spacecraft, namely polar and image. In the old times when image and polar were operational, that could take the simultaneous images of aurora in both hemispheres to show how asymmetric the feature is, both in spatially and temporally. And as you can see in this Nature paper written by Carl Lundell and Nikolai Ostgaard, they basically said that they see a big asymmetric auroral signatures, not only the bright intensity, but also the spatial structure, and such a differences in the internal magnetic field of the Earth or conductivity difference cannot sufficiently explain the asymmetry that we see in auroral signatures. So here in this talk, we'll be talking about asymmetry in MI coupling processes and why that's happening, that I'm going to be talking about. But where that is happening, basically, I have to just throw the famous, really widely used figure that everybody uses. Like it's basically happening everywhere, including current system, particle precipitation, ground pulsations, auroral images. Uh, Basically, you can name everything, even including atmospheric processes. So if you go to CEDAR community, then they talk about interhemispheric asymmetry, even atmospheric community, I'm sure they talk about north-south asymmetry due to neutral wind and stuff. So in this very simple cartoon that shows perfect dipole, that the perfect Earth that contains perfect bar marginet, where the field line is really uniform, then everything is symmetric. The particle follows the same field line and then end up being in the same conjugate point all the time, so no problem. So it has been assumed that our understanding of our one hemisphere can be simply mapped to the other hemisphere. However, we know that this is oversimplification. So now we have a dipole offset. See if the bar marginet of the Earth is not spinning spinning around the Earth in the same angle. So it has some dipole offset that introduces some asymmetry. And now the spin axis also has some tilt angle with respect to the elliptical plane. So that's another complexity. Now this is a very quick and dirty way to describe the non-dipole nature of the bar marginet of the the Earth magnetic field. So then, in particular, the magnetic apex pole is more than 8.5 degrees farther from the geographic pole in the south. So basically, you're not talking about the straight, nice looking bar marginet. So it's a little bit just curved or distorted bar marginet. So that polar region in the southern hemisphere, then as a result, experience a larger daily variation in sunlight as the Earth rotates. Now, because of all of these, then now we can talk about conductivity difference between the two hemispheres. And the source should be solar illumination, of course, and precipitation due to auroral activity, but that can be much more local effect compared to solar illumination. But those two, in combination of those two, can contribute to solar atmospheric conductivity difference. Now, the other thing that we should not forget is the fact that north is basically majority of the space is taken by the ocean, as opposed to the big chunk of ice in the Antarctic. And so atmospheric asymmetry due to different polar vortex dynamics can be introduced. So that affects thermospheric neutral particle dynamics. So neutral wind can contribute to the asymmetric asymmetry between the two hemispheres. So here I just put polar bear in the south, and there's another asymmetry, animal asymmetry, polar bear in the south, north, and penguin in the south. And surprisingly, since I've been deployed to Antarctica many times, I asked, like, have you seen polar bears? Polar bears and penguins cannot be a friend, actually. So yeah, when you walk the door, maybe you forget everything, but one thing you should forget, polar bears don't live in the south. All right, so that's sort of internal source, more or less. But then there's obvious external source. The major player is IMF orientation. So depending on where the reconnection occurs, that can control asymmetry very significantly. Here, so in this talk, and overall, the major cause of interhemispheric asymmetry, especially in GEM community, includes IMF orientation, including BX or cone angle, BY, or clock angle, and solar illumination, which causes conductivity difference between the two hemispheres. So that's here. And then another thing that we should not forget is the fact that internal magnetic field is also by nature is asymmetric. So where that's happening, as I said, everywhere, pretty much everywhere, including large scale currents, aurora forms, plasma convection, magnetic field perturbations, outflow, GPS, tech, scintillation, thermospheric wind, etc., etc. So in this paper written by Londoletto, 2017, showing, I think for Zoom people, I have to use this mouse. There's a internal field. So using IGF-12 model for 2015 at Earth surface, north-south, there's significant difference between the two hemispheres. And as you can see, north-south intensity difference is quite significant in as well as the inclination angle. And the plot on the map on the right shows the polar the magnetic apex location differences between the two hemispheres. All right, so this paper done by Xingzhi and Baldwin, 2024, conducted interesting study by comparing swarm spacecraft and with the IGF model to show where the residuals are found. So as you can see in the middle two plots here, this is north and south occurrence rate of residual field defined as observed magnetic field minus IGF absolute value. Whenever there's a value greater than 300 nanotesla, they show this plot. And especially at higher magnetic latitude, you see more asymmetric configuration between the two hemispheres. And then look at the A index, the relations to A index, and then they concluded that the asymmetries may not be caused by external drivers. So this study basically mainly focuses on the internal effect of asymmetry by comparing swarm spacecraft and IGF model. So you will hear whenever you talk to anyone who does asymmetric studies, they will talk about IMFBY all the time, a lot of time. IMFBY is probably one of the major popular contributor to causing asymmetries. As you know, the convection pattern, you will see the dawn-dusk asymmetry due to IMFBY orientation. But then if you look at the asymmetry between the two hemispheres, not dawn-dusk, then because of this field line tension difference between the two hemispheres because of the reconnection location, then this type of dawn-dusk asymmetry is going to be also introduced north-south as a north-south asymmetry. The basically magnetic tension and pressure, magnetic tension here, and then pressure term in the Lorentz force creates asymmetric current from the lobe, from the tail lobe, that basically causes asymmetric polar cap convection. And this shows the IMFBY magnetospheric BY induced by IMFBY, which causes asymmetric auroral intensity between the two hemispheres, north and south, using polar and image spacecraft. Basically, this paper shows the asymmetric auroral intensity. However, this might be a little bit confusing because now, as time progresses, you see less asymmetric features because of reconnection in the tail. So asymmetry was introduced initially because of the BY, and then later on, the tail reconnection rate increases, then the study concludes that because of the tail reconnection rates, the asymmetry is reduced. Now you see slightly more asymmetric features. And Oma's paper supports later on, he actually published another paper to support this idea in using a lion feather LFM model simulation. So that supports the actual observations of evolution seen in auroral interhemispheric asymmetry. This is another interesting way of looking at interhemispheric asymmetry utilizing only ground-based magnetometer in both hemispheres, utilizing lots of magnetometer network in Greenland, Canada, and US here. And of course, compared to the Northern Hemispheric configuration, we still have a lot of missing gaps in the South, but we were able to, in this James Wagon paper, he used a spherical elementary current system method to produce equivalent current utilizing ground magnetic data to show convection patterns between the two hemispheres, to show IMFBY control of asymmetry, to show the convection change pattern in two different hemispheres. Another mechanism that can control north-south asymmetry is BX. Basically similar concept. BX component controls reconnection location of the location. However, in this case, north-south, north and south. And because of this larger tension force, in this particular case where IMFBY is positive, and then that causes larger tension force in the south, on the other hand, that causes a larger R1 current in the south. So that difference in tension force gives rise to a current generator, causing more stronger current in the south. So interhemispheric differences in auroral intensity seen in the dust sector, as you can see here, because of the enhanced R1 current, can create a dust sector, a higher activity in dust sector, assuming that the current carriers are precipitating electrons. All right, so this paper, another paper that shows the auroral intensity asymmetry between the two hemispheres, north and south. This particular example shows the auroral asymmetry in terms of EIMFB-X component control mechanism. So the interhemispheric differences in magnetic field of the Earth, again, and conductivity difference cannot sufficiently explain the auroral intensity difference between the two hemispheres, as you can see here, and not only in terms of spatial scale, but also temporal scale. And in this particular case, dominant IMFB-X can cause this asymmetry, meaning a stronger solar dynamic effect in the solar hemisphere. Therefore, the more persistent dusk aurora in southern hemisphere. So interhemispheric community always talk about conductivity difference, no matter what causes that. Here, so interhemispheric current system is introduced due to conductivity difference. So first, in this case, northern hemisphere is under sunlit, and then southern hemisphere is less sunlit or dark. Then no significant ionospheric currents occur in the winter hemisphere, as you can see over here, due to low ionospheric conductivity. Then there's another current system is established called interhemispheric current, because north-south are connected via highly conductive magnetic field lines. Therefore, interhemispheric current system is established that flows out of the summer hemisphere and close ionospheric winter part. In that case, you will see much lower R1 current system, but however, there's like interhemispheric current system is more enhanced. So interesting consequence of the existence of the interhemispheric current is that auroral events can be observed not in the hemisphere with the incident field line currents from a magnetospheric source, but in the opposite hemisphere where the interhemispheric current system is more enhanced. This figure actually shows a lot of things. Magnetic pulsation comparison between the two hemispheres, north and south, showing diurnal variation and also seasonal variation due to dipole tilt, dipole offset, the conductivity difference between the two. So you can see not only the intensity difference, but also the seasonal effect and local time effect as well. And they also said antiphase relations between the two hemispheres between interhemispheric conjugate points are due to difference in sunlight illumination. In this Ampere study, using monthly average Birkeland currents measured by Ampere spacecraft data, Ampere project from 2010 to 2012, they also see clear seasonal variation in northern hemisphere. The red is northern, and then blue is southern, and then pink shaded area indicates northern summer, and then blue shaded area indicates southern summer. The clear seasonal variation is shown in northern hemisphere and peaks around northern summers. This trend is less pronounced in southern hemisphere, and the reason the discrepancy between the two hemispheres in terms of field line currents intensity is not really well explained in this paper. And they try to show, excuse me, they try to show this observation in comparison to model by incorporating the conductance and solar auroral activity, and they still were not able to reproduce the observed discrepancy. And they may say that this may be the effect of the asymmetric Earth magnetic field or TEC differences between the two hemispheres. And the recent study provided by Kang Lu and Anthea Costa recently showing really remarkable asymmetric TEC asymmetry between the two hemispheres during a storm even near equinox. The TEC in general is more enhanced in the northern hemisphere, and the asymmetric response of the ionospheric TEC following geomagnetic storm is not, they conclude that it's not really well explained yet. However, Kang Lu's suggestion is that this is likely due to neutral winds. So again, as I said, between the asymmetric neutral wind can contribute to significantly MI coupling as well. This study done by Gabi Nowak and Doha Öztürk from University of Alaska Fairbanks, showing the ground perturbation utilizing ground magnetometer conjugate network, bottom plot here, north and south, and try to compare with Ampere spacecraft field line current configuration, showing the entire local time distribution. And sometimes you see, where there's a high activity in field line current system, then you see ground perturbation, but that's not always the case. So that's what they are trying to find out what causes that discrepancy between the two hemispheres. And they also see the time differences between the two hemispheres in terms of response. At higher latitude, approximately 50% of perturbation peaks occur within 5 minutes in each hemisphere, approximately 10% within the same minute. However, at lower latitude, more perturbation peaks occur within 5 minutes in each hemisphere. So then, yeah, you can see the more detailed study actually tomorrow or today. The poster will be presented by Gaby today. So please come see the poster. Okay, so this is another powerful aspect of having ground facility in both hemispheres. So as you can see on the left panel here, this is the stack plot latitudinal layer range, stack plot of magnetometer data in Greenland. And our team is trying to establish more extensive conjugate network in Antarctic to see this kind of pulsation, ULF wave, magnetic field variations in both hemispheres. And also you can see some traveling convection vortex signature. As you saw in the previous slide done by James Wagan showing convection pattern solely using magnetometer data, you can see the convection pattern between the two hemispheres and then where the convection is happening, where the center is, how fast the convection is moving, where the center of the convection, which corresponds to the field line current system location. So this is the one way to look at the MI coupling asymmetry. And the plot on the right showing emic wave propagation from between north and south utilizing ground magnetometers, surgical magnetometer network to show intensity difference, polarization difference, the spatial and temporal scale of the magnetic emic wave event. Also, we looked at the subsystem signature using this the same magnetometer conjugate network. Sometimes you see similar subsystem signatures, but however, in this particular example, showing some really different, even polarity, showing maybe different electrojet direction, polarity, westward or eastward direction. But in this particular case, some H symmetry was introduced, especially in association with transient clock angle change, especially BY and BZ component. So this could be related to simply I'm a peak clock angle, or as Otani suggested, maybe there could be conductivity, which can play a role in changing the local electron precipitation, which determines the polarity of the subsystem electrojet direction. So here I mentioned simply 4 different mechanisms: internal magnetic field, tilt, offset, etc., IMF BX, IMF BY, and therefore conductivity difference. However, if you have any other suggestion that can control interhemispheric asymmetry, please let's share. My knowledge is, of course, limited. So if you have any other mechanism that can control this asymmetry, we can talk about it too. So why care? Simply speaking, that can impact our understanding of energy deposition into the ionosphere from solar wind, energy budget calculation in modeling. So therefore, we need to have a better understanding of asymmetry. A lot of models still cannot address all these detailed asymmetric features. So, and also a lot of challenges in augmenting the facility in the south observationally. So our understanding is still very limited. In this study, using 4 years of DMS-BSCAP data done by Doris Knipp, showing significant pointing flux differences between the two hemispheres, concluding that the pointing flux difference can be attributed to the solar illumination. Again, conductivity seems like plays a very significant role affecting asymmetry, therefore energy deposition into the ionosphere. The recent study done by Biloco showing utilizing global MH simulation, showing quite different pointing flux, therefore Joule heating. So he actually integrate this pointing flux over the same conjugate area to show the 1 hour energy deposition asymmetry is seen between the two hemispheres, 73 terajoule versus 79 terajoule. Another Joule heating simulation, but this study done by Austin Smith and Doha Orstuk, recent paper showing the Joule heating difference between the two hemispheres, Joule heating and oral heating between the two hemispheres, represented by the two different colors. This basically, the Joule heating is highly correlated with solar insolation between the hemispheres. They are very well correlated. And using GITM model, they show remarkable difference in terms of potential between the two hemispheres, and TEC difference and Joule heating difference, therefore. But the major contributor could be solar insolation. So, summary, community effort. So I've been running focus group from 2018 to 2023, thanks to a lot of people who participate in our focus group activity, including Bob Lysak and Matsuo Tomoko. And CDAR also has been really active in terms of looking at asymmetry coupling process, especially IT process. And NASA LWS program also facilitates a focused scientific group, interhemispheric asymmetries in the MIT coupling processes. This year is going to be the last year. The focused scientific team includes 7 project teams, so it's pretty active and very broad, including CDAR and GEM communities. And I don't know if Dan is here. CUSIA, Center for the Unified Study of Interhemispheric Asymmetries, CUSIA team was formed. I don't know what the current status is, but I think there's a website is still up, so we can see what's out there. EC team, which I lead, that also we 7 countries, scientists representing 7 countries are involved to discuss MIT coupling asymmetry. And of course, I believe this Friday, ground magnetometer committee members will get together to discuss ground magnetometer facility under the umbrella of NSF, so that we, in an effort to augment the observing capability in the south. And Zonghwa Su, Mike Hottinger, and myself organized a workshop called Geoscoper, Geospace Exploration and Observation with Scientific Collaboration in Polar Regions toward IPY, International Polar Year 2032. That was actually sponsored by NSF. About 70 people gathered in Virginia to discuss the current status and challenge, mainly logistics issues, which I will talking about slightly later. If there's any other effort, community effort, please share so that we all know, we are aware of what is going on in terms of interhemispheric asymmetry study. So moving forward, so above the ionosphere, ideally, if you have spacecraft that can look down the ionosphere, as was done by polar spacecraft, image spacecraft, which produces a lot of interesting paper about auroral intensity asymmetry between the two hemispheres, that would be ideal. If I think there is some ongoing effort to make this similar thing kind of happening, but I don't really know the current status is in terms of spacecraft mission. Ground base, yes, there are a lot of course, one easy thing you can think of is auroral skies, all sky imager. If you look up, then you can see the asymmetry. The challenge is that, yeah, you don't really have many days of dark condition in both hemispheres. Once in the south is dark, then the north is dark, bright, vice versa. So auroral imagery on the ground is, of course, is quite highly limited. Then there are extensive teams who try to augment the magnetometry in the south. As you can see, the map of Antarctica showing international effort to augment the observing capability in terms of magnetometer network. So US is highly involved in this international collaboration to expand the observing capability. Rheometers can be very good alternative to say, not alternative, but it's a very good way to measure electron precipitation without worrying about this weather condition, as opposed to all sky imager. So we are also trying to put more rheometers in Canada, Greenland, and Antarctica. And I myself also trying to put a couple of rheometers in the south too, including South Pole, McMurdo Station, and one of those German stations. Of course, radio frequency receivers that can measure VLF, ELF, HF, LF, all these radio frequency receivers can see or part of the auroral activities or Whistler waves or chorus waves. All these wave activities can be sort of picked up by these receivers. That can also be a good way to have interhemispheric configuration. Of course, in-current scalar radar, support down all this like the radar measurement that can do remote sensing of the ionospheric convection pattern. GNS receivers that can measure TEC and scintillations. So we have currently we are trying to expand this ground-based facility in the south to facilitate these interhemispheric asymmetry studies. In terms of model, interhemispheric effects in particular, which is critical to development of valid global models, are generally lacking in various numerical models. Personally, I don't do models, so correct me if I'm wrong, but if you look at the CUSIA CAM capability assessment matrix, as you can see in this link website, you can see all of the asymmetric parameters that you can think of, potential currents, IMFBX component, cause or manifestation. All of these things are listed, and if you click, then you can see. If you click one of these, for example, asymmetric ionospheric potential, then you can see all this description, what causes it, what effect is it, and you can see the modelings that then facilitate this type of studies, and you can, which model has which parameter, which model cannot have this certain parameters and stuff. So you can actually see which model can do certain things or not. So I highly recommend you to take a look at this capability assessment matrix that's done by the CUSIA team, which is really amazing. Dan is not still here. I'm advertising Dan's work on behalf of him. Okay, so to summarize, interhemispheric asymmetry occurs due to both external, including solar illumination, IMF orientation, and internal, Earth magnetic field asymmetry, dipole offset tilt drivers. The assumption that the north and south are mirrored does not address the discrepancy found in observation and modeling work. Still largely unknown are drivers contributing other than BYBX or conductivity differences or internal magnetic field, drivers contributing to asymmetries and their relative contributions in the complex intertwined system. And augmenting interhemispheric observing capability is needed, for example, Antarctica. Various global models that can address interhemispheric asymmetry effects need to be developed to further our understanding of interhemispheric asymmetry. So I'll stop here. I'd like to thank you very much for listening to my talk. Before I go down, I was told to advertise this AGU session that focuses on interhemispheric asymmetry led by Qingyu Zhu. I don't know if he's here or not, but also Lin Harvey, Yue Deng, Dan Welling, and Yunju Chen. Yunju Chen is here or not? Anyway, so yeah, there has always been AGU sessions that focuses on interhemispheric asymmetry. So please pay attention to what's been proposed and make sure you submit your proposal to this kind of sessions. Thank you very much.
The student moderators want to come and help with the microphones and such? Hey, Jodie.
Yeah, really enjoying your talk, and I feel I learned something. The asymmetry of the hemisphere, and also related to what we have been working on, is like the energetic particles. They follow the magnetic field. You show very nicely this is not a dipole, not even just like north and south, are very different. So my question, or what do you have comment among the driver for the ionosphere for this? Not aurora like 100 EV, KEV, but I'm talking about like tens of keV, hundreds keV that can penetrate in deep and can have some MI coupling. And you mentioned about the rheometer, but the rheometer is basically like more integral integration of the total electrons participation. Just I'm wondering your comment on whether those energetic electrons, I'm talking about 30 keV, hundreds keV, MeV, would they have any contributions to the ionosphere, particularly asymmetry? Because we know they are asymmetric. South normally have much more precipitation than north. Yeah.
Well, I do not have really direct answer to that, but I'm pretty sure the asymmetry caused by particle precipitation can be contributed by all this wide energy spectrum, all the way from low to high, including relativistic electrons and stuff. Especially from the ring, the R1, R2, the current system that is highly asymmetric, that can be connected to the ring current and then radiation belt dynamics. Of course, then there should be asymmetry. However, I don't know how much we can actually see those type of things given what we have right now. I know there's some study done by like maybe Benelin probe group to look at this radiation belt dynamics in relation to asymmetry, but I'm not really sure what details or aspect of high energy particle precipitation asymmetric features have been studied. So, yeah, but that's a very good question. Yeah.
topic. And yeah, just because you show that there's some comparison between North and South in terms of ground-based magnetometer observations. Just like to make a comment, especially to all the audience, that don't think that we have enough observations, just because some people already made studies on them. Because if you look, if you look at a map, and figure out the available ground-based magnetometer stations in North and South, I think the available conjugate observations are mostly at very high latitude. But when you go down to auroral latitudes, where you'll see very different auroras between North and South, actually there isn't much ground-based magnetometers that we have in the right places in Antarctica that can make the measurements. So that has been, I think you know this very well, and also Mark Lassar and I have been thinking about this, like, having more observations in West Antarctica. That's really key to make the conjugate observations with our partners in Canada. So just want to bring the attention to the community that actually we don't have enough observations at very critical latitudes just yet. So it's a very important topic for us to look into, and making sure that we're putting the resources at the right place.
Well, thank you for bringing that out, Peter. Basically, the reason why he mentioned West Antarctica is because that particular area was proposed as part of the ground geospace facility, is because that is where the simultaneous nighttime auroral observation can be possible. That's if you look at the geometry or geographic location, that is where you can have most days of auroral observation possible in both hemispheres. So it was proposed, but it never happened. One thing that I like to mention is the fact that right now the Antarctic project is in great danger in terms of logistics support. Right now, there's almost zero logistics support. Of course, the main reason is that the McMurdo station is under renovation. So, and also currently no one is able to, I mean, not no one, but very few people is able to go down there and do even the simple service, the instrumentation. So as Peter pointed out, the augmenting the southern hemispheric observation capability is very important. The other thing that you have to keep in mind is that northern hemisphere, the majority space is dominated by water. So wherever we want to have some ground facility, there's no place. Of course, radar system, for example, SuperDAN, you can have remote sensing, so you don't really have to be there. But there are certain systems, for example, auroral imager, which has to be under the same magnetic field line. It favors certain locations. Therefore, the land space is very important. Antarctica is one of the spaces because it covers a lot of very large area of polar cap. So Antarctica is a very important place. So.
Yeah, following Peter's comment, I'd like to mention that conductance is very important, but for given number or for given location of ground station, conductance is usually determined by the solar zenith angle. And the solar zenith angle is also a function or relevant to dipole tilt. So it's very difficult to distinguish the effects of solar zenith angle and the dipole tilt. Dipole tilt also affects MI coupling and the solar wind manosphere coupling. And so based on statistical study, it's very difficult to distinguish two effects. But if you have instantaneous observation in northern and the southern hemisphere, we can address, based on instantaneous measurement, a global distribution and the effect of conductance and the dipole tilt. And so simultaneous observation based on global coverage is, I think, very, very crucial for understanding interhemispheric asymmetry.
Yeah, thank you, Shin. Yeah, yeah. So just to add, how much do we know conductivity, right? How do we get conductivity value more reliably, right? Observationally.
Very nice talk. I was recently in Europe for a PhD defense, and it's lot of interest in terms of the comment that Shin-Lin just made, the deep penetration of the radiation belt particles into the southern hemisphere, where during the winter, the polar vortex is really very well set up, and the changes that go on with nitric oxide as a result of the particle precipitation is very, very evident in the southern hemisphere. It's because of that very tight circulation. So there's very interesting climate implications
Correct.
for this. And so I think it's behooves the community to know that these asymmetries trickle down, not just trickle down, but they're very evident even in climate.
Yes. So as Dolores mentioned, Antarctica is full of chunk of ice. So that creates like bigger, more active polar vortex, which can create a lot of like climate differences between the two hemispheres, which can attribute to MI coupling process. So very important comments. Thank you.
One last comment. Thank you for the tutorial. And I just want to advertise that although there are limited observation available, but now we do have more than a solar cycle magnetometer data at a conjugate location, both in West Greenland and what Hyomin just showed in the Antarctic, covering polar cap, polar cast, and the aurora zone. All these magnetometer data are available through SIMI's Ground and Virginia Tech website, and also Superman. So if you are interested to look into some ground magnetometer data, yeah, they are available there. And if you have any question, you can reach to Hyomin or me. Thank you.
My Apple Watch keep telling me like time to stand, so I have to finish. Thank you.
Yeah, thank you so much, Hyomin. I actually never knew that the dipole was not just a straight line like through the earth. So I learned a lot from your talk. All right.